Welcome to problem solving session for Introduction to Group Theory course. I'm Siddhi Balu Ambore from IIT Gandhinagar, and today we will solve problems related to syllabus from week 11, that is problems related to symmetric group, alternating group, simplicity of alternating groups, and the sign map. So let us start with our first question. Question 1, that how many elements of cycle type 4-2 are there in the symmetric group S6, and our options are 30, 25, 72, D is 90. So this is the question, and I hope you all know what is cycle type. So, so if so let me just explain what is cycle type. So if we take any sigma in Sn, then we can write sigma as a product of disjoint cycles. So any element sigma in Sn can be written as product of disjoint cycles. Then we say that sigma is of type L sigma 1, L sigma 2, L sigma k, where L sigma I is length of cycle sigma I. And note that if I can write, if sigma is equal to sigma 1, sigma 2, sigma k, then we can shuffle this and see sigma i's are disjoint cycles. Then we can switch the order of sigma i's. That won't change the sigma. So what I'm saying is that here I can write it as some 2 sigma tau k, where I am now choosing this tau in sk. And this permutation of sigma i's, or what I can say shuffling or reposition of sigma i's, will not change the sigma. So in general, Sn is not abelian group, but once we have disjoint cycle, we can commute. So 2 disjoint cycles commute in Sn. Okay, so that's how. So in short, this L sigma 1, so that's why this L sigma 1, L sigma k is with the number of, this will be is equal to number of some length of L sigma tau 1 and L sigma tau k and so on. Okay, so what I'm saying is that writing, so if we take, suppose this cycle 1, 2, 3, 4, 5 in S5, then this is equal to writing this as 4, 5 and 1, 2, 3. Okay, and so So since we are discussing the example, so this has length 3 and this has length 2. So this, if I call this sigma, then sigma has cycle type 3 2 and or 2 3. It's the same thing. Okay, it won't change because both represent the same sigma in, yeah, both present same sigma in, just a sec. Yeah, both represent same sigma in S5. Okay, so that's the thing. So now we are asked that uh, this and yeah, and note that when we represent this sigma is equal to product of disjoint cycles, this we and when we say that something is of some sigma is has a cycle type some tuple, then this, so in short what I am trying to say is that here this summation of length of sigma I must be equal to n. Okay, we are not skipping or what I can say, we are not omitting any i's when we write sigma n or the some element, I mean j's from the set 1 2 3 up to n. Okay, so here this is of cycle type 2, this is cycle of size 2 cycle, this is 2 cycle, this is 3 cycle, so 2 plus 3 is 5 as we are considering this sigma in S5 here. Okay, so this is some uh, basic definition which I wanted to discuss here. And now we will go back to our question, that is we have to find the number of elements of cycle type 4 2 in S6. So we have to find number of elements of cycle type 4 2 in S6. Okay, to find. And how to find. So for example, if we want to take example, then it is, so this is of cycle type this 4 2 sigma and cycle type here is 4 2. Similarly, I can have this 2 3, I mean we don't have to have. Okay, so these are all elements of cycle type 4 2 and now we have to calculate the number of such elements. So how to proceed with it? Any guesses? So here we have options of 4 cycles. So we have, this is like choosing all 4 cycles from S6. And here I want all 2 cycles of S6. And I have to check what exactly I get the resultant number, like how many possible such elements are there. And so there are total 6 factorial elements. Okay, and so there is this formula for this to calculate. Formula to find number of elements of cycle type of given cycle type. Okay, so what we exactly do is there. So if I have, so for example, when we write this, just an example, okay, please, this is like for understanding. So if I consider, so if I take S8, okay, in S8, for example, if I am considering um, elements of cycle type 5, 3, so there is only, I mean, whenever I take cycle, that cycle will contribute only once here. But if I take something of this kind, 3, 3, 2, then if I take this element 1, 2, 3, 4, 5, 6, and 7, 8, this and this element 4, 5, 6, 1, 2, 3, and 7, 8, they are actually same. I mean, they are equal. They both represent similar sigma in S8. Okay, so we also have to take, so when we are writing formula, we are considering all the possible cases we might have for this, for sigma in Sn. So we also have to take care of such things. So if I start with, so to calculate this sigma, I have this sigma, then here, this is sigma n factorial will be my total cycles. Then here, if I take, so here I will represent it as 3 square 2. Okay, this 3, 3, 2, let me represent it as 3 square 2. So if I have cycle of this type, uh, let me just, how, so if I write this, that this is my N1 represents size of a cycle, and this, so N1 represents size of a cycle, and K N I, and Ki represents the uh, the repetitions of Ni size cycles in given cycle type. I will just explain what I'm writing here. So for example, if I take this 3, 3, 2, this is my cycle type. So I will represent it like this, 3 square 2. Okay. So this Ni represent cycle types, and Ni not equal to Nj for all I not equal to j. Okay, I'm considering distinct sizes now. Okay, so when I consider this Ni is distinct, then I can club the same, and at the end, what I have here, that summation Ki Ni is my n. Okay, so it is still a cycle type, but we are writing it in compact form. So here my N1 is 3, N2 is 2, K1 is 2, and K2 is 1. Okay, so my N1 is 3 and Ki is power of 3, N2 is 2, power of 2 is 1 here. And so formula goes like this, that number of cycles, sorry, number of elements of cycle type, this n1 power k1, nk power, sorry, what, nr, ns power ks is in Sn is n factorial divided by this k1 factorial up to ks factorial, n1 power k1 up to nk power ns power ks. And why this is? Because this n factorial by k factorial s factorial, this is, we are choosing these elements. We are choosing the cycles. And then we have to divide this here, n1 power k1, nk power k, ns power ks, to avoid the repetitions of the cycle. Like here, that permutation of two cycles was still giving me the, not the permutation, I mean switching the cycles, we have to calculate the number of elements, right? And if two, I need to get rid of extra number of elements which represent same element in Sn. I mean extra expressions of a given Sn of this type. So we in give the given element sigma in Sn can be represented as in various ways, as product of transposition and so on. And a given cycle, if we permute, and disjoint cycles we permute, they actually represent the same. And when I take this n factorial over k1 factorial, ks factorial, so on, I'm just choosing, I'm just calculating the number of such cycles in S in Sn, which has size 332, or which has size n1 up, which is of size, I mean, this is of cycle n1, n1 cycle, n1 cycle, this k1 type, then n2 cycle, this k2 type. This is a really bad notation, but I hope you understand what I'm trying to say here. Ns, this ks type. So when I write this here, this here, it only gives me such elements. And here when I write this nis, it doesn't what I can say, it doesn't differentiate between when I shuffle these n1s here. So for example, this is n1, this is n2 here, then this n1 2 and n1 1 here, this number won't differentiate those elements. So that's why I need to divide it by this n1 power k1 ns power ks to get rid of those extra elements of this kind. Okay, and what are, I mean, how many such elements are possible? K times, right? N1 power k1 and so on. I hope you understand what I'm trying to say here. Okay, so that's the formula. This is the formula. If you do not know, let me box it. Okay, so this is the formula. So what we have, so let's get back to original question here. Question was to calculate, to find number of elements of cycle type 42 in S6. So here what I will, so this by formula, if I call this number A, so A is 6 factorial, and this 42 here, there are two types. So this is N1, if I want to write this in this form, N2 power K2, Then my N1 is 4, N2 is 2, K1 is 1, and K2 is 1. Okay, and so this divided by from the formula, this is K1 factorial, K is factorial. So that is 1 factorial, 1 factorial, N1 power K1, N2 power K1. So this is 4 power 1 and into 2 power 1. Okay, and this is 6 factorial. So let me write this. 4, 3, 2, 1 divided by 4 into 2. And this is 6, 5, 3 into 2 and sorry. Yeah, 653, that is 90. Okay, so that's how we calculate the number of cycles in S6 of this type 4-2. Okay, so I hope this was clear here. And if so, here the answer is this 90 is the correct answer here. Any doubts here how to calculate? Or if you want, we can try one more example. Here N1 and K1 were same, but let us try to do this. Suppose we have to calculate just for understanding the formula. Just calculate elements of type 332 in S8. Okay, so this is equivalent to writing this as 3 square 2. I mean, this is just a notation. This doesn't actually mean we are squaring anything. So here N1 is 3, N2 is 2, K1 is 2, and K2 is 1. Okay, so this is N1 power K1, N2 power K2. And the formula is elements of cycle type 332 in S8. So now this is in S8, okay? I mean, remember that the summation of L of sigma I must be equal to N. And so this is N factorial. K factorial is 2 factorial, 1 factorial. And then N power K1. So this is, yeah, this is 3 square and into 2. So this is 8 factorial. Here we are in 8. So this is 8 factorial divided by 2 into 1 into 3 into 3 into 2. So this is, let me write this completely. 8, 7, 6, 5, 4, 3. And when I'm doing this, I'm getting rid of this 3 here, this 3, this 6 here, and 2 here. So this is 8, 8 into 7 into 5 into 4. And this is, this many elements are there in, this many elements of type, cycle type 332 are there in S8. Okay, so that's how we need to, I mean, we can directly use this formula to calculate that. But note this, how these Ni's and Ki's are there, and just represent first the sigma. So you can also be asked to So let us just go to next question. So in general, if you are appearing for the exam, the another way of asking similar kind of question is uh, they might give you a cycle, which then you will have to, I mean, the question might be like this. Let me just write the question here for possible question, just question that how many uh, elements are there in essay S9 of cycle type of same cycle type as let me just write this below. Or they can just give you whatever something of this kind 8 6 5 4 2 3. And in that case you will first have to write this in disjoint cycle form and so on, and then you will have to find like what is the cycle type of given sigma and then calculate it's something like this. Then you have to first find out the cycle type and then calculate the given sigma, or they can also give this in two cycle form of, let me just keep of this time or something like this which I wrote here. I hope I am 6875 yeah. Or they can give two layered, this two row cycle form 1 2 6, and then anything of this sort. And then first you will have to find the so in this case they have actually given the disjoint cycle, and this is anyway a disjoint cycle. I mean, this is only one cycle of 8, so that's not a problem. But yeah, something like this is already giving you what is the cycle type and so on. But here you actually need to find what, I mean, you have to convert this two row expression of given sigma in asset to cycle form and then club them the same number of cycles and so on, like we need for the formula, and then calculate the number of elements of that certain cycle type. I hope this is okay. I mean, I consider this imperfect. This is, understand, this is 8 cycle. That is a cycle form in itself, and this is disjoint cycle form, and this is two row cycle form. I mean, you need to know how to express given cycle in any of this form, and how to obtain the original form, other form from the given form, and so on. If you don't know, please practice it. And now the next question. Yes. Question 2, like what is the order of the following permutations, permutation, and this is the permutation 1, 2, 3, 4. Okay, this is in S9. And options are 7, 14, 6, and 12. So since we are given this in two-row form, we first need to convert this into cycle form. Because note that when we have something in cycle form, then it is product of elements in Sn. And we know order of our cycle is R. And so it's easier when we take the powers in that case for those cycles. In disjoint case. So whenever we are asked to calculate the order, do not directly go for the multiplication. Convert that into disjoint cycle, and then we can just use the GCD and LCM of orders smartly and obtain the order of given element. So for example, here if we want to calculate, if we are converting this into cycle form, let us call this sigma. So cycle form of sigma in cycle form. This is 1 goes to 2, 2 goes to 7, 7 goes to 5, and 5 goes to 8, and 8 goes to 3, 3 goes to 4, and now 4 goes to 1 again. So this is closed here. And now 1, 2, 3, 4, 5, 7. So now 6 and 9 are remain. So 6 goes to 9. Okay, and here the order is, this is 7 cycle, this is 7 cycle. So here order is 7, and this is 2 cycle. So order here is 2, right? So if I look at sigma as, if I give them name sigma 1 and sigma 2, then if I want to then I can write sigma as product of sigma 1 and sigma 2. And note that since these are disjoint cycle, they commute. So here the product of this sigma 1 and sigma 2 is also equal to sigma 2 and sigma 1. So what we can do in such cases? So we know that if if AB is equal to BA, then order of AB is order of A into order of B divided by GCD of order of A into, order of A and order of B. I hope you all remember this formula. This formula works only when we have when the elements commute. Okay, in general, this does not hold. Okay, please understand that. So, yes. So we have this here sigma 1 and sigma 2 commute because since disjoint cycle implies sigma 1 and sigma 2 commute, then therefore using this formula we can find order of sigma to be order of sigma 1, order of sigma 2 divided by GCD of order of sigma 1, order of sigma 2. and that is just 7 into 2 by 1, that is 14. Sorry. So this is the correct answer here. 14 is the order of this sigma. So if anywhere, if you are given if you are asked to calculate order of given sigma, convert it into R cycle and then calculate it. It would give you what I can say. It's easier to calculate the order that way. Okay, if you have any doubt, uh, please ask. Otherwise, we can move to next question. So now next question. Question 3 there. Consider the symmetric group S4. Let sigma is equal to 1, 2, 3, 4 in S4. If tau is in S4, that commutes with sigma, which among the following is a possible cycle type of tau? So, and options are first. Options are 2, 2. This is 3, 1, 1, 1, 1, 1. And fourth is just 4. So, what are your guesses here? How to proceed? And when we are saying that sigma commutes with the tau, note that since given that we want to find the type of tau, so sigma commutes with tau. This implies that sigma tau is equal to tau sigma, right? So this implies that tau sigma tau inverse is sigma. So this is actually what we are saying is that tau is something which fixes sigma under conjugacy action. Okay, and when that happens, uh, the number of cycles here and number of cycles in tau, they must be of similar kind. Okay, so here when we have this sigma, sigma is 1, 2, 3, 4, and then if I want to write them in the transposition form, it is 1, 4, 1, 3, and 1, 2, right? So wait. Yeah, let me. This is 4 cycle. Okay, this is 4 cycle. And this is actually this when we write this 1111. This is just identity element. Okay, this is just 1, 2, 3, and 4, and permutation. So this is anyway identity permutation. So definitely this will be the type. That's not a problem. And this one, but if you consider this will be 1 3 cycle. This will be of this kind, some A, B, C, and D. So this is 3 cycle. And if I want something to commute with the tau, then that won't be possible because here we have something of odd order, and here this element ABC here is of order 3. And we have seen that if we represent elements in cycle form, then that if sigma and tau in same are conjugate, then and if I write sigma as sigma 1 to sigma r, and here it as tau 1 to tau s, then r must be congruent to s mod 2. Okay, so they must have kind of same parity, but here that is not happening. So here we have order 3, and so this one is not possible. Here too, again, we have 2 transpositions. So they won't so they again have this same parity for 4. So that's why this one will again commute with sigma and any 4 cycle, and its inverse will again give back me the tau. So it will again commute with this sigma here. So you just need to check the order of the elements and how they represent when we convert them into cycle form. Okay, and you can check this with the examples that you can take any element which commute with the sigma and check its cycle type and how it works. And if you, so the possibility of those elements will land in this cycle types only. And if you choose any element of this cycle type here, it can never give you, it can never commute with our given sigma. That is this cycle 1, 2, 3, 4. Is this okay? There are many theorems which are proved in, I think, in lecture, which helps you to understand all this uh, questions here. So any doubt here? If not, then we can move to next question. Okay. So next, so let's move to next question. I mean, this kind of questions again, if you are giving exam, you can do this by just working with the quick examples, and you will arrive at the conclusion. Okay. So yeah, so let's try to do this question. Question 3, that which of the following is our true? First one is two cycles, that is transpositions, generate the symmetric group Sn for n greater than equal to 3. B, that two cycles generate the alternating group An for n greater than equal to 3. C is three cycles generate the alternating group for n greater than equal to 3, and D is none of the above. So we just have to check for this three, A, B, and C part, which of them is true. So second one, that first one, that two cycle, that is transpositions generate symmetric group Sn for any n greater than equal to 3. This is anyway true. I mean, from in the lecture itself, we saw that, right? And not only this, we also saw in the lecture about simple transpositions. So this set of two cycles in Sn is huge set. Okay, they are like in Sn, there are n into n minus 1 by 2 transpositions. Okay, so this is huge number. So, but note that we in the, I think, theorem or proposition in the lecture where we already proved that any sigma in Sn can, I mean, Sn is generated by all the transpositions n. Oh, sorry, all the transposition in Sn. Okay, and how to do that? That what we first proved, the proof goes like this, that what we showed, that any sigma, we can write it in this form. Sigma, I mean, what we do is, if I have sigma, I write this sigma in cycle form, sigma 1, sigma 2, and sigma k. And each cycle then, so if sigma 1 is of this form, what to write? Oh, each of them is a cycle, right? So we can write them is this form, sigma 1, sigma S1, 1, sigma 1, 2, sigma S2, 2. This is not really good expression, but yeah, sigma 1k, sigma S, kk, and so on. So if we are writing this, then each of this cycle here, this sigma 1, 1, sigma S1, we can write this in this form, as a product of transposition, sigma 1, sigma S1, sigma 1, sigma 1, sigma S minus 1, sigma 1, sigma S, sigma 2, descending. So what we are saying that if I have this cycle A, B, C, yeah, some just example, then I can write this as AF, AE, AC, AB. That's it. Okay, and these are all transpositions. So what we are doing is we can write each element in Sn as a product of transpositions. So collection of all those transpositions will generate the entire Sn, because what does it mean when we say that something, a given set generate our group G? It means that product of those elements is enough to generate my entire G. So that's what transpositions are. What we proved there is that any cycle of size R can be written as product of R minus 1 transpositions. And the moment we have that, the given sigma, when we decompose it in the product of disjoint cycles, each cycle, or even in general cycles, each cycle will be product of transpositions, and that will ultimately give us that sigma is a product of transposition. So uh, yeah, so that's how the proof went if you go through the lectures. So therefore these two cycles generate the symmetric group is completely true. Okay, and so this is anyway true. Any doubts here? I mean, I hope you all have been through lecture. I mean, even if you have not, I mean, if you are still confused about this thing, note what does this, if you want to check this, this starts with A, right? A goes to B, and now B is fixed everywhere. So A goes to B here, right? And then we start with C. Wait, start with A. A goes to B, B fixes everywhere. So A goes to B. Now here B goes to A, and now I'm starting with B. Here B goes to A goes to C, and now C is fixed in these two cycles. So I have C here. Now where does C go in this product? C goes to A goes to E, and now E is fixed in this cycle. So E, and now E goes to A here, and A goes to F, and now F anyway goes to E here. So this was the original cycle. So I hope you all know what, uh, I mean, I'm just telling that this product actually gives me the given cycle which we started from. So in general, if I want to write this, some A1 to AK, then this is transposition A1 AK, A1 AK, A, and A1 again, A1 AK minus 1, A1 AK minus 1, A1 AK minus 2, and the product continues till A1 A2. Okay, and further we also in the lecture saw that the set of all the transposition is too huge, and we can just reduce the, so instead of considering whole of transpositions, we saw something like simple transpositions, and which said that we can generate Sn using simple transpositions. Simple transpositions are transposition of this type, I plus 1. So Sn is generated by I plus 1, such that, no, this was correct, I plus 1. Okay, so this was just a recap from the lecture. And so in general, we know that Sn can be generated by 2 cycles. Okay, so we have this, and now this one, that 2 cycles generate alternating group An. Is this true? I mean, can someone tell me like why? I mean, why this statement is true or false? Do you think that 2 cycles generate alternating group An? I mean, if you don't know alternating group An uh, is collection of all odd cycles in Sn. It is group generated by all odd cycles in group Sn. So, and when we say something odd cycle, it means this. Or when I say no, collection of elements of odd order. Okay, and it is also called as elements which are product of even number of transpositions. Okay, note that why only this forms group, that collection of odd order groups, and why do not we consider something as collection of even order groups, is because this forms subgroup of Sn, and if I want to talk about subgroup, I must have identity element there, and order of identity element is 1. So we must consider elements which are of odd order. Okay, so they are saying that 2 cycles generate alternating group An for n greater than equal to 3. Is this possible? And if yes, how? And if not, then why? Any understand that 2 cycles means 2 cycles means transpositions, right? And if I say something generate my group, that element itself must belong to that group. But transpositions do not belong to does not belong to AB does not belong to AN for any transposition in, because it is collection of elements of odd order. AN has order of AB is 2, so it does not belong to, therefore AB does not belong to my AN. So if something does not belong to group itself, we can't talk about it generating that set, because that does not make any sense. Because if AB belongs there, then AB into identity, suppose AB is a generator, then identity is there, so AB into identity must there. I mean, in short, if element itself does not belong to that group, that cannot be one of the generators. So two cycles definitely are not the generators of AN here. Okay, please let me know if there are any doubts. And now the next question, that three cycles generate alternative group for n greater than equal to 3. And what is your guess for this? That do you think that three cycles generate alternative group for AN for n greater than equal to 3? First of all, three cycles belongs. First, that note that three cycles. See, but that any ABC order of ABC is 3. So any three cycles belong to AN, right? It contains all the even permutations. Even permutations means a permutation which can be written as even number of transposition is called as even permutation. Okay, so these even permutations, though they have odd order, they are called as even permutation because they are product of even uh, number of cycles. So note that any, how to prove this? Any guesses here? So ABC anyway belongs to AN, as AB, it is product of AC and AB, right? So what about other permutations? Note that any permutation sigma in AN is product of product of even number of transpositions, right? So if sigma is what? Sigma is product of some, if it is product of A1 B1, A2 B2, and it will be some A K B K, where this K is even, right? So since K is even, I can club each of this. I don't care whether they are disjoint, whatever form they could be, whether they are simple transpositions or any transposition. The definition is that they are product of some even number of transposition. It could be repetitive, it could be disjoint, it need not be disjoint or any sort. We just have the information that they are product of even number of transpositions. So I can just club this like A3 B3, A4 B4, and similarly so on up to A K minus 1, B K minus 1, and A K B K. Right? I can club these two always. And if I can show that any such product of two transposition, I can write it as a product of three cycle, then we are done, right? Because then each such tuple, if I write this as some product of, what I can say, just a second. Yeah. As a product of three cycles, some A, B, C, E, F, D, doesn't matter. Just product of three cycles, then I'm done, right? So we will do that. We will try to express this in terms of three cycles. So note that if this is of this form A1, B2, then this is just A, B2, B1, right? So we are just omitting the pairs where we already have such kind of form. So what I will do is, so we claim that product of any two transpositions can be written as product of two, product of three cycles. That's our main goal. Doesn't matter how many number of cycles, product of three cycles. And how to do that? So let A, B, and C, D belongs to Sn. Then what we can do is, then we can write this. We claim that this is equal to this A, C, B, and C, B, D. This is the claim which we have. Okay, note that in S3, there are only two cycles. I mean, AN in S3 is this E123 and 132. So we know any possibilities are, I mean, it is anyway generated by 3 cycles here. So we are talking about n greater than equal to 3 here because we already know how things are there in A3. So this, we can assume this ABCD to be disjoint and work, and this then will be, and so let us see how this is. A, B, C, D. A is going to C. D is fixed here. C is, B is going to, A is going to C. C is going to B. B is going to A. And C, A, B, C, D. And here A is fixed. C is going to B. B is going to D. D is going to C. And now let us try to, so how this cycle is. A is going to A is going to C. B is going to D, D is going to D, C is going to B, let us check, B is going to A, and D is going to C, C is going to B. So this is, okay, so this was ACBD. This is AC and BD here. So we got them as product of two tricycles. So if I choose, I mean, you can shuffle and check that, just matter of, so this is exactly what we wanted, that any product of two cycles, we could write them as product of these 3 cycles. And the moment I have that, using this expression here, each of those tuples, I will get, I mean, each such pairing of, let me just choose this one. Each such pair I can write as product of transpositions. And the moment I have that, I get that it is product of 3 cycles. And that's what we wanted to prove. Any doubts here that we just proved that 3 cycles generate the alternative group AN for n greater than equal to 3. Okay, and here please note that this ABCD, when I write here, I assume that they are, I mean, none of them is, I mean, all of them are distinct actually, not equal to C, because otherwise, if any of them is equal, this cycle, I mean, yeah, I mean, we doing it. We definitely need this C and B not to be equal. I mean, at least one of them need not be equal, because then this won't make any sense. Okay, we need to make sense of this. So we better assume that none of them are equal and proceed to do this, because if A is equal to, I mean, transposition. So if A is equal to B, or if A is equal to D, then this is what? This is AC, and if A is equal to B, then in this case, this is this, and wait, this, and I can just write this as A D C. I get this is 3 cycle, and similarly, if A is equal to D, then I have this, right? This BA, and BA I can then write as AB again, because AB is equal to BA. Okay, so this then will be equal to some A. This is A B C. So what I'm saying is, when I am clubbing them in this clubs of two transpositions, if one of the element, so if I am considering this as one of, if this is my AI, BI, AI plus 1, BI plus 1, if any of the AI plus 1 or BI plus 1 is equal to any of the AI or BI, then that directly becomes a three cycle, and we do not need such expression in that case. So when we are clubbing them, those where one of the element coincide with one of the element from the cycle next to it, those club, they by default get clubbed as a three cycle. So to write them in this form, we are choosing these ABCDs are all distinct. I hope you are getting what I'm trying to say here. Anyway, A is not equal to C, and I'm assuming that AB is not equal to any of them. This condition here is kind of necessary for this to make sense here. Okay, so we just proved this, that so alternative group is actually generated by three cycles. So any doubts in that? Okay. If there are no doubts, then we will move further. But understand that what we did here, we already in the lectures, we have proved this, that two cycles generate Sn. But for An, we need three cycles. So An is a subgroup which is generated by three cycles, and we just proved, and in fact, we gave explicit expression. Just like the proof of proving that any element in Sn can be written as product of transposition, we explicitly give how we are actually going to express given sigma as product of three cycles. And they are like this. So when I write this, it means that this A1, B1, A2, B2, I am actually writing that A1, B1, A2, A1, sorry, B1, A2, B2. We are just expressing each of this tuple of that kind. Each of this is now product of three cycles, and let me just write it here. What we got, that it is A1, B1, A2, B1, A2, B2, and so on. So that's how we actually represent any given sigma in alternative group as a product of three cycles. If there are then any doubts, please let me know. Otherwise, I will move further. About this, that all these need to be distinct, and if one of them coincide, then how we can club them, and so on. If not, then I will move further. And okay. So we have to calculate. So question, this is question. This is question 3. So this is anyway on. This is question 4. That hmm, okay, so we have to find the sign of this permutation. So sign of permutation. So if we write, we know that definition, that is sign of permutation. So if sigma is product of sigma r, where each sigma I is a transposition, then this sign of sigma is -1 power r. Okay, so all the elements in alternating group have same sign, and that's even. Okay, so even permutation means elements in an are sign have for for any sigma in an, sign of sigma is 1. And all the rest elements have sign -1. So for example, every transposition is a uh, odd permutation and it has sign -1. Okay, and note that the moment, I mean number of, yeah, I mean this is a theorem which we have. If sigma is product of transpositions where each ei and tau, sorry, each sigma I and tau I, tau j are transpositions, this is theorem, then R is congruent to S mod 2. Okay, so if I'm writing, so sign is what I can say is an intrinsic property of given sigma. It does not change with the way we are representing that sigma. The sign always remains same. Okay, so yeah, so sign of sigma is -1 power r, where r is the number of transpositions required when we represent sigma as a product of transpositions. Yes, so what we need to do is, in order to write this, find the sign of this permutation, we need to first write this as a product of two cycles, and then we will calculate, we will count how many transpositions we need to write this. Yeah, so here 6 is fixed. Let me just check the transposition. Doesn't matter, but still. Yeah. So if I want to write, first let us write this in the cycle form. And since 6 is fixed, we can omit it. So 1 is going to 2, is going to 4, is going to 5. and now 5 is going to 3 and 3 is going to 1. So this is 5 cycle, and now we will write them in the form of transposition. So 1 3, 1 5, 1 4, 1 2, and that's it. So these are 4 cycles, 4 transpositions. So therefore, if this is sigma, then sine of sigma is minus 1 power 4, that is just 1. So sine of sigma is plus 1. Plus 1. Okay, we explicitly write them as plus 1 and minus 1, not only just 1 and minus 1. Okay, so yes. Any doubts here? How to do this? So this was 5 cycle. So note that in general, any odd cycle has positive sign and any even cycle has negative sign, sign minus 1. So any odd cycle has sign plus 1. Any negative cycle, sorry, any odd cycle has sign minus 1. That's why sign of a transposition, not that's why, I mean sign of transposition is minus 1. So from the convention, we are doing that. Any doubts here? Like how we are calculating the sign and everything? Mhm. No, then okay. Yeah. We'll try to prove this. Wait. Yes. This is a prove means it's a quick observation that this is question 5, that let n greater than equal to 5, then every 3 cycle in an is a product of permutation cycle of type 2 2. And this is true or false. Any So what they are saying is that every 3 cycles, so any A, B, C in AN, it is product of, so what they are saying is it is product of permutation cycle of type 2 2. So what it means that this A, B, C is product of this 2 permutation. Let me just write them in this form. Sorry. Alpha 1, beta 1, alpha 2, beta 2. It's not, or let me write now. Even F1 E2 F2 and E3 F3, E4 F4. So this is 2-2 type. This is 2-2 type. And what they are saying is that any 3 cycle in AN for n greater than equal to 5, we can write it as a product of 2-2 cycles. And how to then prove that? Or any proof or any counterexample that some AN cycle cannot be written as product of 2-2. But first of all, the baseline understanding is that if at all we are trying to write any sigma in the form of transposition. So when I'm writing this 2-2, it is product of transposition in general. So any sigma of type 2-2 is product of two transpositions. So they have sign even, right? Because it is 2 cycle. And here the 3 cycle also has sign +1. So both these elements have +1 sign. And they are saying that it is product of permutation cycle of type 2-2. So when they say that this anyway has sign +1 and we are writing it as product of this +1 type cycles. So it will again be some element of psi +1. So in short, what I'm trying to point out here is that if you are writing exam and if you are asked such kind of questions that some K cycle, whether it can be written as some ABC type cycle, then it's important for you to check that it is possible only when that both those expressions have similar sign. Otherwise, it won't make any sense. Okay, so in order to first, so this is like baseline checking which we need to do in order to proceed with the understanding whether this statement is true or false. Okay, so we have this. So let sigma be some ABC in AN. And since we are in here, n is greater than equal to 5. Since we are in a n where n greater than equal to 5, wait, we can choose E and F, which is, sorry, D and E, which is not in this set ABC. So we are just choosing extra elements, the remaining elements, or any two elements which are not equal to this ABC. Then we claim that this ABC is this ABDE into DE DEAC. Okay, so now this becomes then 2-2 cycle. Okay, and this is quite easy because see, what is this ABC? This is ACAB. And since we are talking about transposition, I can just write this, right? Identity and this AB, and but identity, let me write here how to write identity here. So this is AC, this is DE, this is DE, and this is AB here. I think I made a mistake here. This will be AC, this will be AB. And that's it. We now this is 2-2 cycle and this is now 2-2 cycle. So this was quite easy. Just quick check. We just had to insert this DE here to write that expression. And even if you do not need this DE, we can just, no, in that case it won't, right? Yeah, I mean, that would also, no, it won't. Yeah, we need this to be 2 type. So this needs to be disjoint here. We can't repeat the element. So what I'm saying is that this ABC, I can write this as AC and AB. That is okay. But we can just do this here. AB and A, yeah, whatever. When we can't say that then this is 2 type. That does not make any sense. When we say that this is 2 type or some given sigma in Sn is some K type, some tuple type, then it the baseline requirement is that we are expressing that in disjoint cycles, and then we are then we are calculating the numbers of, no, then we are counting the number of I mean, then we are reading this, then we are checking the size of that cycles when we are writing them in a form of disjoint cycles. Okay, so I hope this was okay. And that's why we need this n to be greater than equal to 5 to make sense of these things here. Otherwise, it won't make any sense to declare that this is 2 cycle. Because even if we take n is equal to 4, still we can't express that. We will not have this as 2 type cycle there. Okay, any doubts here? This was quite easy. But yes, any doubts? Okay, if not, then we will move to next question. So this is question, I think, 5. Yeah, question 6. That let sigma and theta be to 3 cycles in an for n greater than equal to 5, then they are conjugate in an. So this is the question, and again we need to check true or false here. Theta is just, we are, so in general what we are saying is here is that 2 3 cycles in an are always conjugate of each other, because see, we are fixing sigma is varying here, and if 2 elements are, I mean, the conjugacy is transitive action, if you remember. So if sigma is conjugate to theta and sigma 2 is conjugate to theta, then sigma 1 and sigma 2 will be conjugate of each other. Okay, so what they say is that this sigma is three cycles in AN are conjugate. And we are just fixing this 1, 2, 3 here by calling it theta to make the calculation easy. Okay, so let me just use this one. So let pi be a permutation in Sn such that this pi sigma pi inverse is equal to theta. Okay, so we are starting with this conjugate, that since pi and theta are conjugate, we will try to produce now this pi, how it looks. So if this pi is even permutation, that is pi is product of even transposition, then we are done. Right, because then sigma is 3 cycle, it is of 2 type, and sorry, it is of even type, and so we have that theorem, if you remember, that two permutations are conjugate of each other if they are of same type. So sigma and theta are 3 cycles, so they are of same type. They are of, yeah, they have the same cycle type. And if pi is also a even permutation, uh, then we are done using the theorem which we proved in the lecture. But if if otherwise, or else, if not, then choose K and L which are not in this 1, 2, 3, like we did in earlier. Here n is again greater than 5, if you notice. 1, 2, 3. And since theta and tau commute are disjoint, wait, yeah. So and we call this tau KL. Since theta and tau are disjoint, this implies that theta and tau commute, right? We just saw even in the beginning of lecture that if I have two disjoint cycles, they commute. We in fact use that to calculate order of the element which was asked to calculate. So if we have disjoint cycle, they commute because none of the element interfere with the, what we can say, uh, cycles of disjoint kind and so on. I mean, understand this, that two cycles, if they are disjoint, they commute. And we have this information. So then this tau theta tau inverse will be theta, right? Because then tau theta will be theta tau, and then this tau theta tau inverse will be theta. So hence, if I take this, that pi tau, product of this pi and tau, theta, pi tau, wait, yeah, inverse is pi theta pi inverse. I'm just multiplying. So this will imply this 3 multiply by pi, or left multiply by pi and right multiply by multiplication, what it, and this will give me this, and that is equal to pi tau theta, pi tau inverse. This is pi theta, pi inverse, and sorry, this is tau pi inverse. But this, if I replace this, this is sigma pi theta pi inverse. Does not matter much. So this, that's why I get this equal to sigma. So therefore, so this imply that pi tau theta, pi tau inverse is my sigma. And note that pi is odd permutation. Wait. Yeah. Note that this pi is odd permutation and theta is from the choice. Since we omitted the condition of pi is equal to even. So if not, that is pi is odd. So I have this pi as odd permutation and theta is anyway transport and tau is equal to KL is transposition. So is also odd permutation. Then this pi tau is even permutation. So I have even permutation such that it conjugate with the theta and pi. So therefore, such that it conjugates sigma and theta. Hence, we got that they are conjugating. So hence we get that sigma and theta are conjugates in AN as pi tau belongs to AN. Okay, so we produced an element of AN such that it commutes with, it conjugates theta and sigma. So the question was that it is conjugate, that then they are conjugate in AN. We anyway know that when we proved, in fact, in the lecture that any two cycle type of same kind, they are conjugate in SN. Here, what we said that two, three cycles are conjugate of each other in AN. And when I say that, I need to produce an element such that it conjugates theta and sigma. So what I did was that uh, if I find some pi which is even permutation and such that this pi sigma pi inverse is equal to theta, then we are anyway done. But if this pi inverse does not have even permutation, then if that pi is not even permutation, then we try to produce element this pi tau like this here, which is even permutation and it conjugates sigma and theta. And we did that using this. We chose this tau here, which is not in this 1, 2, 3, and we obtained this. And 1, 2, 3 here does not play any role. You can just take any ABC and still proceed with the proof, and it will be similar. Then you just have to choose this KL not in that ABC, and we will be done. Okay, so we just proved that any two cycles, any two three cycles in AN are conjugate in AN. Is this okay? I mean, any doubts? If not, then we'll just. Or we can just, I will just state this theorem here, and I will try to, you can try to prove it. This is, so this is true. Okay. And here, this statement was also true. This question 7 here, that let H be a subgroup of order bigger than A4 uh, bigger than 4 in A4, then H is equal to A4. We'll try to see how much we can do with this. But this statement, this again, we have to check whether this is true or false. And this is true. Okay, and we will try to prove this. So, or you, or or you can just try to prove this. Okay, try to prove this if you do not know. And we will now, since the time is not there, we will do this one, and this we will try to, I mean, please try this, and if you have any doubt, please raise this in the discussion forum, or we can prove this in next week's session, or yeah. So question is, this let that does A4 have subgroups of order 2, 3, 4? Okay, so A4 is, S4 definitely has groups of order 2, 3, 4. That's not the question. The question is, does A4 have, so we know what is A4, right? Order of A4 is 12. But now we are asked that whether it has any element of order 4. See, any group of order 12 need not have a subgroup of order 4 in it. You can produce such a group, and or if not, then maybe that will be isomorphic to A4 then in that case. But or may not. But right now the question is that A4 will have a subgroup of order 2, A4 will have subgroup of order 3. The main question is that whether it has a subgroup of order 4 or not. A4 is a bit, what I can say, A4 has all the even permutations. So we have to now generate a group which has size 4 in A4. Okay. So note that the permutations 1, 2, 3, 4. I mean, in S4, we could have just take this cycle 1, 2, 3, 4. In S4. In S4, we can choose 1, 2, 3, 4 this cycle, and this cycle will give me an ideal a subgroup generated by this cycle has cardinality 4. So it will have subgroup of order 4 in S4. But note that this does not belong to A4. Okay, this is product of three transpositions. So this is odd permutation. But we are in A4 and we are dealing with even permutations. So note that cycles of this form 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 2, 3 are the only elements in A4 of order 2. Okay, you can check that. These will be the only elements because we do not have any other option because uh, permutations permutations have order 2. Sorry, transpositions have order 2. And the only possible elements in A4 which has order 2 will be this product of two permutations or product of two permutations, two disjoint permutations. So note that if you have permutations sigma 1 to sigma k, not permutation, transpositions, disjoint sigma is, or let me write it here, why there. If sigma is, note that if sigma is sigma k, where sigma I are disjoint transpositions, then order of sigma is 2. Okay, because now these are elements which commute and you can just proceed with that definition, I mean the formula for order where we know how to calculate order when two elements commute and so on. So we will apply that finitely many types using induction or just recursive process, and you will get an order of sigma is 2. So the only possible elements in A4 with order 2 are these. Okay, these are even permutations. And each set this identity permutation and this every element 1, 2, 3, 4 identity with this 1, 3, 2, 4 and identity with this 1, 4, 2, 3 are the only possible subgroups of order 2 in A4. Okay. And for three cycles, so for order 3 groups, I mean, we can just choose any 3 cycle in A4, right? 3 cycles. We know that 3 cycles generate. 3 cycles generate. Yeah, 3 cycles generate A4. We know that, and so we can take any 3 cycle, and so choose. Then say tau. Then subgroup generated by tau will have cardinality 3. Okay, it's a 3 cycle, then order of tau is 3. That will be the order of subgroup generated by that tau. So we have now subgroups of order 2, subgroups of order 3, and now we need to calculate subgroups of order 3. And okay, so we now have learned the formula of, so use the formula to calculate how many, formula in question 1 to calculate how many order 3 subgroups or order 3 cycles in A4 are possible, are there. Okay, you can use that n factorial and so. So when I write 3 cycle here, it has this cycle type. And you know the formula to apply. So this you can use as an exercise. Wait, I hope it works. Doesn't matter, but try to calculate this. And now the last one, that wait, we have to now find the group of order 4 there. So since, so let H be this group identity, this set identity 1 2 3 4, 1 3 2 4, and 1 4 2 3. Okay, then one can check that. Then H is a subgroup of order 4. Note that each, so this is subgroup of, so this is set of order 4, right? The only thing which we need to check here is that AB inverse is in H again or not. Okay, and note these, all these elements here, these are those elements of order 2 which we calculated for obtaining subgroups of order 4. Okay, sorry, subgroups of order 2. So it's enough to, so if you take product of, so inverse and the element are same, the elements are self inverse. So if I do this 2 4, you can calculate, and that, and the, yeah, we can't, right? Yeah, we can't. 1 2 3 4, or let us try this. Since this is 1 2, this is what, this is 3 4 and 3 1 and 2 4. So this is 1 2 3431 is, no, it's not helping. We just have to calculate it this way. And 1 goes to 1 here, 1 goes to 3, 3 goes to 4, 4 here, 1 goes to 4, 4 goes to 2, 2 goes to 2, 2 here, 2 goes to 1. Okay. Okay, we are making, okay, we started with 4, 4 goes to 1. Now 2 goes to 4, wait, yeah, 2 goes to 4 here, 4 stays, 4 stays, 4 goes to 3, and 3 will go to 2 here. So this is 1, this is 1, 4, 2, 3, and this definitely belongs to my H. And you can check the other. So this is like our, so H is actually isomorphic to our clean 4 group. Okay, clean 4 group. And you can check that this is the only possible order 4 subgroup in A4. So yes, that's it. So this we will try to prove next time or maybe after that. And meanwhile, you can try to prove, please use the formula which we learned to see this. And apart from that, I think, any doubts? If there are any doubts, so therefore H has order 4, and so A4 has, so answer is yes. So any doubts here regarding what we did today or anything from the lecture or other? Means we are over time. If there are doubts, we can solve. Otherwise, we can end the session. Okay, if not, then thanks.